So I realized that I completely forgot to pass around the samples of what I was talking about before. So we're going to start with a few pass-arounds, so they will hopefully help you. This is more the old style of a wide flange, or an I-beam in its shape, but you get the idea for kind of weight of steel because this is a fairly hefty piece. So be careful when you pass that one around. This is just steel plate, but again, it's pretty good to give you an idea of weight of steel. This is a hollow section steel that happens to be round. If we look really carefully, we should be able to find the weld, but of course, I think it's right here. It's right there. So it can be somewhat challenging to find it, but you guys get the idea there. This would be an angle. This would be a channel, just from a size perspective. And then finally, I do have a piece of cast iron, just for food for thought. You can tell that it's been broken, and you kind of get a sense for what that is. It is clean, so you don't have to worry, even though it's pipe. So we will continue on from there, but I did want to make sure that you got to see those. It's my fault for not getting them done. I also have all the tests graded, and you'll get them back at the end. If I gave them back to you right now, you wouldn't pay attention to a thing I talk about because you'd be looking at what you missed. So that's why you don't get them right now. But at the end, you'll get them. I will also tell you there's a few questions that when I went through and made my answer key, I didn't really like, so I'll give you hints that those might be the good ones to argue on. Right? So let's continue on. We will cover trusses more in depth next class, but we're going to certainly start on trusses today. The first type of truss that we'll talk about is what's called an open web steel joist. Okay, so by joist we're meaning that it's on the smaller scale of trusses. It is a mass-produced truss, and the idea of a truss is basically that we're going to use small pieces that are spaced relatively closely together to support the same amount that a large beam would have to support. Right? So we're using smaller pieces, and we're taking away more of the non-working structural elements to make these, right? And so, for example, right, this is one of those open web steel joists, right? These, right, would be the top and the bottom flange. This would be the top flange. This would be the bottom flange. Each of these diagonal and straight pieces are serving to keep those two top and bottom flanges apart. So, to give you an idea of what these guys can do, a K series can span 60 feet, right? It's somewhere between 8 and 30 inches in depth. Right, so it's reasonable in depth. An LH series can span 96 feet, and it's going to be 18 to 48 inches in depth. Right, so the depth is definitely getting much deeper. Right, and a DLH series can span 144 feet, and it's going to be somewhere between 52 and 72 inches in depth. Right, so that's my height. Right, at the larger end. Well, a little bit under my height at the larger end. So that's a much, much deeper beam than we're talking about. And at a certain point, it would be too dense if that was a solid beam to actually be able to use. So we're going to try to take out some of that those non-working elements and replace them with lighter weight elements. Right? The spacing between open web steel joists, so in terms of the density that they're put together, they're somewhere between 2 feet and 10 feet. And that's going to be determined based on the load that's up top. Right? So whatever you're trying to support is going to determine the density of how closely spaced these open web steel joists are going to be. Right? So if we look up here, don't look at the first bit, right, because that's the false ceiling. They're going to put those little funny ceiling tiles like this in. Right? But we're going to go up a little higher, and we'll see the open web steel joists there as well. So for the fun of it, since we're talking about trusses, we're going to take a field trip into the room that's next door to us. Right? What? I don't know. It's a Google. Okay? So we're going to go right through here. So these aren't entirely steel trusses. I'll wait until everybody gets in here. Okay, so these aren't entirely steel trusses at all. But the concept of the truss still exists in this building. That's how we're spanning the distances we're spanning in this building. Okay? The bottom chord and the top chord are both wood, right? And I would invite you all to stand on the tables, but then you'd fall off and sue me, and we can't have that, right? So I value my life too much for that. So no suing me, right? But you can trust me, this is wood, not steel, right? These diagonals, however, are steel, right? And they're pinned together right here. There's a little bit of a hole that I can stick my finger in, right? That's pinning those steel pieces together. So chances are you've been in this room before and you probably haven't looked up past the lights, right? But this exact ceiling, right, is filled in the next room over, right? So we're not seeing the trusses. In this room, we're seeing the trusses. So the same concept happens. Notice how deep these are. These are probably about 5 feet, right? They're not spanning from this wall to that wall. They're spanning from this wall across both rooms to the far side. Okay? So it's a much longer span, and it's part of why we can have such an open room in the room next door, the drafting lab, is because it's supported with trusses above. Make sense? Right? And really, these are relatively lightweight pieces. You know, it's a couple 2x6s with some steel separating them, and they're spanning that large of a distance. Okay? So let's go back in the other room. It was a short field trip.
There's no trusses over there?
No, there are trusses over there.
But not this.
Yeah, they're the same as this. They're just covered up.
Oh, that's why the span.
Mm-hmm. Exactly. Yeah, it'd be much better if it was exposed, right? Acoustically, it's not as good. So if you look up in this room, right, you can see where the trusses are, right? Those little brown pieces, right? But we have the tiles that are infilled. And it does certainly help with the acoustics in this room. It makes it slightly better to have the acoustic tiles, okay? So this ceiling is that temporary ceiling that we're seeing here. Above that, we have our trusses. So you have to kind of look through that particular image to see the trusses. So we move up from the open web steel joists to what are called joist girders, right? And this is a prefabricated truss that's designed to carry much heavier loads, right? And it's going to be somewhere between 20 inches and 72 inches in depth, right? It's often used instead of a wide flange, right? So we take the wide flange out, which is really heavy, where the depth is okay. So we can carry a lot of weight, but we're part of the sacrifice of using one of these, which costs less than a wide flange, is that we're sacrificing depth. So we have to have a tall enough space to be able to have a truss. So for example, in this room, we can have a 5-foot truss and the ceiling's still very tall, right? So it works out okay, but we have to have that space to use, okay? So this is a good example. It's hard to see, so I'm going to stand up here and actually point at it, right? So we have to look up really high. The open web steel joists come up these sloping pieces here, right? When we get to this end, there's a column. This, right, is that joist girder truss. Does that make sense? Much deeper, much heavier, right? And the open web steel joists are smaller, and this would be an open web steel joist. It's bigger, but this is the biggest, right? Which is how we get to the joist girder. Okay? So in drawn format, the joist girder would be running this way. The open web steel joist would be running this way. Right? So the joist girder, which can support more load, is then supporting all of the open web steel joists. Okay, so how do we connect pieces together? And I apologize, I'm going to have to keep taking drinks in between because I'm going to lose my voice momentarily. I can feel it start to go. So we needed a way to fasten steel together, right? So the first way builders came up with was called a rivet, right? And the idea of a rivet is it's a steel fastener, right, that consists of a cylindrical body and a mushroom-shaped head on one end, okay? And so what they would do is they'd heat those up on site, and once it was nice and white hot, so really, really hot, right, they'd insert it through the holes, right, the holes in the two opposing members, right, and then they'd hammer the other side with a pneumatic hammer, right, and once they created a mushroom head on the opposite side, so once they hammered that down, the steel would cool, and we know from steel that as it cools, it shrinks, right, and that would then hold the two pieces together. It's pretty good technology, really, right? So what would happen on the old sites when they were building something like this is they'd have a central place where they were heating up these rivets, right? And the person who was responsible for the furnace and heating them up, right, would take one out with a pair of tongs, and they'd toss it, right, to a person that had like a catcher's mitt on, and he would catch it, right? And then once he caught it, right, he could then put it into the hole where it belonged, okay? So if we think about today, right, it's probably not the best OSHA like guidelines here, right? So we toss this white-hot piece of steel, right, way up on a building to some guy who's supposed to catch it, who's barely balancing, not cabled in or tied on to anything, right? And he's supposed to catch it and not drop it and not let it go past him down onto the street below where it's going to, hit somebody in the head, right? So probably not the best strategy, right? But as it cools, it does actually work to join the two pieces together, right? It's not as precise of a control as, say, a bolt or a tension control bolt, which we'll talk about in a second. So we've technology's made things a little bit easier and a little bit better for us. But that was the first way that large steel buildings or bridges were actually put together. Okay? So today, riveting has been replaced, right, with either bolting or welding or a combination of the two, right, which has become much easier to work on site, right? So a couple other old-time pictures just because it's kind of ridiculous, right? So these guys are up here working on it. Here's an example, right, where they're going to rivet these pieces in, right? They've got the pneumatic hammers, right, to put those together. Notice their platform is mostly air, right, with a few boards, right? And my guess is that these guys probably stand out here, cantilevered out there, and just tell the other guy, well, you stand over there and balance me, right? There's no harnesses, right? There's nothing. There's no safety gear, and yet they were able to build these buildings, right? Yes. Yes, sir. Yes, good. Right in here. Right, underneath so that they could lean out over, right? Because that's a real secure way of trusting that, right? So the point is that, building methods have changed a bit, right? But it's still kind of impressive. So today we're going to primarily join pieces together by either bolting or welding. And so we'll talk about bolts first, right? There are high-strength bolts that are treated during the manufacturing process to develop a greater strength, right? There are lower-strength carbon steel bolts, right? These are the kinds of bolts that you're going to go buy at like Home Depot or something, right? Different grade of steel. Nearly all bolts used in this kind of steel construction are going to be the high-strength steel bolts. And I'm going to pass several of them around. I can start with this. I have to keep a few of these up here because I have to show a specific thing, but here's an example of one of the bolts, right? And there's a couple different types, right? These are the kind of one of the hardest things to understand about steel construction, right, is that there are a couple different types of connections that happen, okay? The first type that we'll talk about is a bearing-type connection, right? In a bearing-type connection, the bolts only need to be installed so that they're snug, right? In this case, right, movement in this particular example is usually vertical loading, just straight down weight, right, is resisted by the bolts themselves, right, as the sides against the sides of the bolt holes, and they bear against each other. So it's one of those things that's so challenging to figure out how to explain, right? So the idea here is that if I had a bolt, right, and I was bolting two pieces together, right, and I had a hole through one piece and I had a hole through another piece, right, in a bearing-type connection, the shear strength of this bolt not being able to split apart, right, is what's holding this particular connection together, right? I'm not applying any kind of weird lateral forces to it. It's just straight down. I have weight resting on one, right? I have another piece that's supporting that. The ability of them not to slide past one another is that bearing strength, right? And so this bolt isn't acting, it's not because I have it tightened down against each other really well. It's because there's a bolt that goes through the hole that's not allowing those two pieces to slide past one another, right? And so if you have trouble understanding that, we'll come back to it a few more times later in the lecture, and hopefully that'll help, okay? So the second type of connection is a slip critical connection, right? And this is that the friction between the adjoining faces becomes important, right? So we're not just relying on the bolt body not being able to slide past each other. We're relying on the friction between one metal piece and another metal piece to not resist, or to resist that force. Okay? So we're trying to tighten these bolts enough so that one steel plate and another steel plate aren't going to be able to, the friction between the two isn't going to allow them to slide, right? Not that the bolt won't break off. Does that make sense? Okay? So in this particular case, which is most common in these types of bolting operations, is that we need to find a way to tighten the bolts to a specific amount, right? So that they're actually tight enough to form this kind of a connection, right? So we'll talk about how the bolts do that, right? The other factor in steel construction, let's go back to the last slide for a second, right? If we're trying to bolt pieces of steel together and there are that many bolts, right, there's some challenges with getting all of the pieces to align correctly so that the bolts can actually go through all the holes, right? So if the holes in each of the members were drilled precisely at the same diameter, exactly what you need to pass this bolt through, right, there's no room for any error, right, in that drill hole. So what they do instead, right, is they give you a 1/16 of an inch larger diameter in the piece that the bolt's going to go through. So if you take the diameter of the bolt, let's say it's 1 inch, right, the hole that they'll drill in the piece of steel that the bolt's going to go through will be 1 inch and a 1/16. Okay? Sounds generous, right? But if you really think about it, that means there's only a 32nd of an inch on either side of the bolt. So it's not that generous. But it does help for some fluctuations in how you drill those holes. And more in today's economy, we're going to use computers to drill the holes rather than have somebody actually out there drilling the holes, right? So they're going to be more accurate, and we can get these kinds of things. Okay? So to span that little bit of a gap, a lot of times there's going to be a washer that's going to go in. The bolt that I already passed around to you has a washer on it, and I'm actually hoarding these bolts on purpose because I need to explain a few things about them. But the washers allow you to bridge that gap, right? Cover up that hole, give you a little bit more bearing surface to attach. Okay? The bolts are going to be tightened with some kind of a pneumatic hammer, right? Or an electric impact wrench, usually, right? In a bearing type connection, right, the amount of tension that the bolt is in isn't really critical, remember, because it's about, one, the bolt not being able to break apart, right? In the slip critical connection, where we're trying to establish friction between the two pieces that are being bolted together, right, then the bolts have to be tightened reliably to at least 70% of their tensile strength, right? So we need some way of determining how tight is the bolt, okay? And so there are a variety of strategies for doing that. The first strategy is called the turn of the nut method, okay? And this is kind of the simplest form. And the idea here is that you tighten up the bolt, right? You keep tightening until it's snug, and then you turn that bolt as much as, or as little as a third of a turn, all the way to 1 full revolution, right? And that extra bit of tightening allows the bolt to get up to 70% of its tensile strength, okay? It's not perfectly accurate because you, as the installer of this bolt, have to be able to determine, right, what is a full revolution, what is a third of a revolution, right? So it's a little bit more complicated to get it precise, okay? The next thing that came out is called a load indicator washer. Ah, good, I have one, okay? And so the load indicator washer has these tiny little bumps on it. You guys see that? I'll pass this around so you can actually hold on to it, right? These little bumps, okay? You guys can pass that one around. Okay? And what happens as you tighten the bolt, right? So there's those little bumps on the washer. As you tighten this bolt, right, the little bumps flatten out and squish down. And when they're squished down, you know that it's achieved its desired tension. Okay? So as those squish down, and I have another one right here. This one has it on it too. So you guys can look on this bolt. There's the little tension indicator washers, right? Once those are flattened off, you know that this has the desired, right, tension. The other thing that's happening, right, is that instead of just having, and I don't have a physical example of one of these, but instead of just having that load indicator washer with the nubs on it, they will actually put little plastic capsules inside those little dimples, so that when they squish down enough, they'll break and release a dye, like a UV dye or bright colored dye, that you'll be able to then check to see if all of these bolts reach their desired strength really quickly and really easily, because they'll be dyed a certain color. Does that make sense? Right? So it's an easy way of determining that they have reached their desired strength. Okay? So the last type, which I have this one, I have this one. You guys can take this one already. Start passing that around. Right? Is called a tension control bolt, and this is probably the most common method today. It's a special type of bolt that once, if you're looking at, let me take the nut off this bolt here for a second. Right? If you're looking at the bolt itself, there's the standard threads of the bolt, right? And then at the end there's this geared spline. Okay? But if you look carefully at the one that passes around, there's an indentation in between the geared spline, right, and the threads. There's a slight indentation there. So what happens when you tighten this bolt, right, is you attach one piece of your special wrench, right, to the spline itself, and one piece of your wrench to the nut itself. And as you tighten this, right, once it reaches its desired strength, right, or tension, right, this little splined end will snap off, right? It'll shear right off. And once that happens, and you can see the example, here's the little splined end. This is what it looks like when it's actually attached. This is a bolt that's already had it stripped off, right? Once it reaches that required strength, the little tip, right, the little splined end snaps off. Therefore, you know it's its desired strength, right? So the bolt is specifically engineered for that purpose, right? And it ends up being a very efficient way of knowing, yes, that bolt reaches its desired strength, right? Much less guesswork. So that's a tension control bolt. Okay? The other option we have, besides just the bolts, is that we can actually weld two pieces of steel together. Right? And we've talked about this several times throughout the class already. Right? But welding can join two pieces of steel as if they're a monolithic whole. Right? In fact, if it's properly done, the weld itself is stronger than the two pieces of steel that it joins. Okay? So the fact that we can take smaller pieces of steel and basically glue them together, right, and make larger pieces of steel, makes steel a really powerful building material. Right? Bolting is certainly easier to accomplish in the field, right, because welding takes so many variables into account, and we'll talk about those in just a second. Right? Often in the field, we're going to use both bolts and welds. Right? The welds where it's really, really critical, right? And the bolts wherever else you can use them, right? Sometimes the designer is going to choose which method to use. Most of the time, the fabricator shop is going to decide how should we make these connections together. And we'll talk about the fabricator next class, right? So what is welding? Okay, and this is, I will freely admit this is not my area of expertise. I'm not a welder by trade. So people that are welders, if I say something, please add to what I'm saying. The basic concept is that there's an electrical potential established between an electrode and the steel that you're trying to weld, right? And that electrical potential, right? The electrode can be held by a person, right? If you're welding by yourself, or it can be held by a machine. A lot of the fabrication shops have machines that do this, right? When the electrode is held close to the steel, the electric arc forms between the tip of that electrode and the steel itself. That electric arc, right, melts the tip of the electrode and the steel right next to it, right, that it's supposed to be welded together, right? The electrode is then drawn across the joint, right, filling up that joint, right, and making that seam with a bead of metal that cools to form the connection between the two pieces, right? So you're heating up the steel on either side, and you're adding metal, right, to form the gap between the two. Okay, so here's our example. There's our electrode. There's our electric potential, right? The arc. It's melting this particular piece, right, and adding to it, right, to create the joint. Welding. Yes, sir. it's designed that way. So the electrode that you're melting is a stronger grade of steel than the steel itself. So by the time you make that transition, so when you melt the steel on one side, melt the steel on the other side, plus you have a stronger steel that you're making with the electrode, by the time you make the joint, assuming it's done properly and there's no air gaps or anything like that, the joint itself is actually stronger than the sides, which is the desire to it, right? So the thing about welding is it's very complicated. You have to determine voltage, amperage, polarity, right? You're adjusting all of those to achieve the right heat, right penetration of the weld, right? Humidity is going to change things. Temperature is going to change things. Wind is going to change things, right? There's a lot of factors that go into making this really precise weld, okay? Often, right, the edges of a weld are beveled to allow the electrode to penetrate the full depth of this particular weld. If that's the case, sometimes they'll use a little backup bar, a little extra piece of steel that helps you make this joint, right, that keeps the ability to go the full penetration, right? And we'll talk a lot about full penetration welds, and I'll show you some actual examples or some drawn examples in just a second to make it a little clearer, right? So a full penetration weld is stronger than a partial penetration weld, right, because the weld material goes the full depth of the two pieces you're trying to join together, right? So example here, okay? We have a V-groove that we're trying to weld and fill, okay? We want these to be a monolithic hole. If we make our weld in between, this is that little backer bar I was talking about, so what you're welding doesn't fall through, right? If we make this weld, we're melting part of the steel here, melting part of the steel here, we're filling with a higher density steel here, right? Makes this whole thing a much stronger piece, okay? If we look at something this, it's a V on one side, we're welding to a vertical piece here and a horizontal piece here, right? This is doing the same thing. It's penetrating all the way through the depth of this material. So it would be a full penetration weld. If we get to the side here, right, same configuration, horizontal piece and a vertical piece, right? We're doing what's called a fillet weld, okay? So we're heating up and melting this side. We're heating up and melting the top bit of this surface, right? And we're making our weld in between at the joint. Notice, however, it's not a full penetration weld because it doesn't go all the way through this piece, right? This becomes a much weaker joint than this would be, right? In this example, it's a monolithic hole between this and this. They're completely joined. In here, right, it's joined across this, but it's not joined at all here, right? So this is a much stronger weld, and it's going to be something we're going to focus on as the class goes on, right? So just remember the term full penetration weld. A couple other examples. Full penetration weld here goes all the way through the two materials. A double bevel, right? Same thing, goes through both materials, therefore it's a full penetration weld. You're just working from one side and the other side, right? Double fillet is not a full penetration, right? Because we have one fillet weld at the top, one at the bottom, but we still have this air gap. Okay? A couple other types. Puddle weld. When we'll talk about this a little bit more as we go along. This is a cold-rolled steel decking that's going to be used for a composite deck topping where we have concrete and steel working together. We want to attach it to a steel frame of a building. We use what's called a puddle weld, which basically means we weld through the sheet steel to the I-beam below, and we just puddle on the weld. Okay? Yes? Spot weld, yeah. Generally, I've heard spot welding. Correct me, maybe the terminology is slightly different. Spot welding is very similar, but it's usually done in a shop environment, and a puddle weld is usually done on a construction site. But I don't know. I could be wrong. It depends on the trade a little bit. Yeah, exactly. The slang term. It's like when we get to wood, I'm going to call certain things different than what the book calls because I'm so programmed to call them that. So we'll get there, right? Partial penetration weld looks very similar to the V-groove weld that we talked about, but notice it doesn't go all the way through. Therefore, it's only a partial penetration, right? Another example of a fillet weld there. No. What I want you to know is the difference between a full penetration weld and a non-full penetration weld. Okay? So the key importance is that a full penetration weld goes all the way through the material and joins the two pieces as a monolithic whole, right? The other type, if it's a non-full penetration weld, right, doesn't join the pieces as a monolithic whole, right? It's a weaker joint. So the connections, right, typically use angles, plates, tees, a transitional element between the two larger pieces that connect, right? So if we're connecting a column to a beam, and this one hasn't been welded yet, for example, right? We have a plate that's been welded onto the column, right, at the fabricator shop with the holes drilled through it so that on the site we can put the beam into place, put the bolts into place, and the building will stand temporarily, right? Long term, we're going to perform a full penetration weld here, and we can see that because of this bevel and this little bit of an air gap between the two, right? So we're going to weld this flange at a full penetration weld to this column, right? There's another little piece here and here. Those are stiffener plates to increase the strength of the joint. We'll talk about those as we go along. So, shear connections, right, join the web of the beam, but not the flanges. Okay? Shear connections resist vertical or shearing forces, but not lateral forces. Right? So this has nothing to do with earthquakes. It's only all of us standing in the room that this is trying to deal with. Okay? It's obviously a much cheaper connection to make because it doesn't involve welds. Right? In this particular example, the angles are typically bolted or welded to the web of the beams at the fabrication shop. Right? The angle is then bolted to the column once it's in place. So if we jump back, right, this happens to be beam to beam, but the concept is exactly the same. Right? On one side or the other, this will be prefabricated on the end of one of the beams. Right? We'll use the angle to transition. We go from web to web. And web, what I mean is that midsection, right? Not the flanges, but the midsection. So it's web to web. Right? And this is just showing you in section the top of the wide flange here, the wide flange here. There's our little angle that goes between and our bolts. Okay? Moment connections, right? Which all of you architects, especially those of you in 220 that are talking skyscraper stuff, right? You need to think about moment connections right now, okay? Because moment connections transmit bending forces, so earthquake, lateral forces, from a column or from a beam into a column. Okay? They don't require any special braces. It's the strength of the weld itself that allows you to transition those forces. Right? So this is something that architects love to use because it can keep your building completely open so that you don't have any diagonal braces on the inside or on the outside. You don't have any shear walls, right? You're using a different type of connection to keep your floor plan completely open, right? In order for this moment connection to happen, the beam flanges must be welded to the column or to another beam using full penetration welds. So it has nothing to do with the webs. It has entirely to do with the flanges. Okay? And I'll show you some examples of that in a second. It's typically done by full penetration welds. Okay? The column flanges, if they're not strong enough, right, we're going to add stiffener plates, something like this, to accept the forces that are being attached to it, right, to increase that strength. So, here's our moment connection in process. Okay? We have our column. It has our full penetration welded stiffener plates, right, where the flanges are going to hit that column, right? Temporarily, we have this little bolt plate so that we can bolt it in place and hold it there. After it's in place, we're going to perform full penetration welds at the bottom here and at the top there, right, so that this flange is welded completely to this flange of the column. Likewise, same thing happens at the top. Yeah, Tola. I couldn't hear you. The bolts will stay there, right? So the sacrifice of the 4 or 5 bolts that hold it in place is perfectly fine. They don't add any strength to the moment connection. They would help with the shear connection, right? Just the vertical loading, but nothing to the moment connection because all of the moment connection is handled by those joints, right? Those full penetration welds. Okay? The other thing that happens is that the flanges of the beams, when it comes into a moment connection, typically have these little scoop cutouts that are called dog bones, right? And those scoop cutouts are basically intentionally weakened sections of the beam, right? Such that in a major earthquake, right, or some kind of extreme lateral load that happens on the building, right, any kind of stress will manifest itself here at the weak point rather than cause cracking at the moment connection, right? Cracking at the moment connection would result in the building to collapse, right? Bending, right, or problems that would happen here would allow the building to stay standing even if it was a little cockeyed, right, or tipped or bent. Okay? So, as with all earthquake designs, it's not about making the building resistant to the earthquake. It's about making the building safe enough for people in an earthquake to get out. Right? So in a steel building, they're willing to sacrifice this beam knowing that they could come back and replace this, right? So that the people and the building will stay standing and the people will be able to get out and be safe. Okay? So that's called a dog bone. The deformations are going to happen at that point rather than cracking the welds themselves. Right? This is what we don't want to have happen. Right? We don't want that cracking. So the building must be able to resist the lateral forces from a wind or an earthquake. Right? We have 3 different ways for that to happen. Okay? The first is braced frames, right, which is very common on building retrofits. It's also very common. You've seen it plenty, and we'll see that in a second. The second type would be shear walls or shear cores, which we'll also talk about. Those of you in 221 have already been talking a lot about cores, so you know that that's kind of a major structural component, right? And we have moment-resistant frames. So what does that do in terms of architecture? Right? The first example is a braced frame, right? It's created through the use of diagonal members, which we talked a little bit about trusses using those diagonal members, but we're using this at the building scale. Here's our building, right? We have our little braced frames happening here, right? Those are then resisting. If I push on this building, right, each of these diagonal pieces, let's say I push right here, right? And this is a simple example. Certainly someday you'll take a statics or a structures class and you'll have to calculate this stuff. But let's just think conceptually, right? I push right here, okay? The force that's traveling along this beam, right, is going to reach this diagonal, right, and transmit down into the ground, right? Likewise, it's actually going to pull on this one too and stretch it, but it's easier to see it in compression where it's going to transmit down. Yes, sir?
On that scale, would they only brace the center, or would they brace more than just the center?
Depends on the actual size of the building. I think this is out of the book, and I think they're trying to simplify a bit. Sometimes you'll actually brace, and we'll talk about, you have 2 options. You can brace the core, or you can brace the perimeter, right? And depending on your philosophy or your architecture, you might want one or the other, right? But it's not necessarily just one bay. It's going to be dependent on the size of the building. It might be 2 bays that you have to do it. Yeah.
The new Kaiser Hospital that I'm going to have there's braces every 3rd bay.
Yeah. Yeah. Most of the time in a building that's in this kind of earthquake country, if we're going to use these diagonal braces, they're going to be all over the place, right? And there are some special types of braces that help with the earthquake loading that we can talk about a little bit later. Okay. The nice thing about this type of bracing system, right, is that the connections do not need to transmit moment forces. So they're not fancy connections. They don't need the full penetration wells at the flanges, right? Because if we simply bolt here and bolt here and bolt here, we're naturally forming a triangle which is resistant to that force, right? Just like making a truss. We're naturally forming that shape. And by doing that, we can bolt these connections together. We don't. Sorry, I told you I'm close to losing my voice. There's only a few slides left, right? So, right? This is a bolted connection. It's a natural triangle that resists it rather than having to have the moment connection. Okay? They behave like pins, right? If you've ever made a triangle and pinned the ends together, you know that's a very rigid form. So, we can have what's called an eccentrically braced frame, and this is where let's contrast that for 1 second, right? These meet in the center. An eccentrically braced frame, right? The braces don't meet in the center, right? And this works out okay for smaller scale buildings. Give me a second to draw this really fast so I can hopefully illustrate it. Right? If we have a brace that comes up here and a brace that comes up here, right? There is this space that can have deformations to it, right? So if we're pushing on this, right? So let's say we're pushing on this, right? It's coming along. This part can bend up, right? Because the brace happens here, or it can bend down depending on which way the forces are acting. Does that make sense? Right? Because there's this gap at the center. So you're not going to see this on extremely large buildings, but on the smaller scale, it can work fine with lower loading. Right? So it's used as a way of absorbing energy in an earthquake to avoid collapse. It's relying exclusively on the same type of connections like the last one was. Okay? The other example, right, is to use shear walls or shear panels of some kind. Right? And we'll talk about shear walls a little bit more when we get into wood construction because they're more common. But the idea here is that we're actually filling one of these bays with some kind of a solid material. And in the case of steel, it's usually either a brick wall or a concrete wall. Right? And so if you're thinking about designing a multi-story building, this is a great place to house an elevator, for example, right? Or something, some kind of building core services, fire escapes, those kinds of things, right? But it's a solid object broken by very few doors or very small doors if it's broken at all, right? And that rigid wall panel is then resisting the lateral load, right? The fact that we have that solid wall, when you push on it, it's able to transmit the forces, right? If I'm pushing here, it's going to transmit down through this solid wall down toward the ground, okay? Obviously, the taller it is and the skinnier it is, the harder it is to resist the loading, right? But we're not in a structures class, so I'm not going to make you calculate any of that kind of stuff. Okay? And the third type of a moment resistant, the third type of a frame is a moment resistant frame, right? And so those of you that are architects look at this and say, "Oh, I like this one," right? There's no shear walls, right? There's no diagonal braces that are getting in my way for views, right? I can have a completely open grid, right, of columns and beams. I can do anything I want in the floors. I'm not having anything interfere with my building design. So that's great, right? And we can actually do this in a building. The problem comes with the cost, right? So in order to do this, we have to make a bunch of these connections, moment-resistant connections, which means we're going to get the pieces to the site, bolt them into place, and then we're going to have to perform on-site full penetration weld at the flanges, right? So there's a lot more welding that's going to happen here and here and here to be able to support this kind of a building, right? And so the cost is higher, but what we get from an architectural perspective is a much more open building, right, that doesn't have anything obstructing our views. Okay? So typically in a building, we're going to have some combination of the two, right? In the world of architecture, we would like to have everything completely open, but we're willing to sacrifice certain diagonal braces to be able to have moment connections in other places. Right? And so we'll use diagonal braces where they're not going to be seen. We'll use shear walls where they can be in a core, for example. And we'll supplement with moment-resistant frames when they're really important. Right? This is all because they cost more. Right? Not all of the connections need to be moment connections. And this is something that you guys already pointed out a little bit, is that not every single joint in the building has to be this kind of piece. We have two different ways of doing this. We can have a rigid core, or we can have a rigid perimeter, right? And so the idea here is we have a multi-story steel building. We have a rigid core that goes through the center. In this particular case, it's a shear wall system, right? But it could be a rigid core that has diagonal braces in it. That's providing the primary lateral loading for this multi-story building, okay? The other option is to move all of those brace pieces outside, and we can either put the shear wall on the outside, or we can put the diagonal braces on the outside, and we can leave the inside completely open, right? So obviously this building isn't a multi-story building, but we've elected in this particular building to have a completely open interior. We don't have a rigid core. Therefore, we have to have our lateral loading pieces on the outside walls, right? And in this case, it's on this wall, not on that wall, right? This building was also built earlier than they were really concerned about all the shear walls that are in it, but it's okay. So does that make sense? Yeah? Okay. So that's it for today. I'm going to stop the recording, and then we'll pass out your tests.